Let me start the seminar. It is my great pleasure to introduce Professor Martina Hofmanova from the Bielefeld University. Martina has huge contributions to, say, virtually all difficult stochastic partial differential equations, with perhaps special contributions to stochastic fluid dynamics. I think she changed our understanding on stochastic dynamics of compressible fluids. And today the talk is about Navier-Stokes equations, Euler equations, and invariant measures. So please, Martina, start.
Thank you, Ben. Thank you very much for this kind introduction. Thank you for inviting me to this seminar. So I want to present what is the very last paper with Ronchen and Chen Zhu, which we put on arXiv just a couple of weeks ago. And this is a culmination of a series of works. This was really a very fruitful collaboration that we started about 3 years ago. And we were interested in stochastic 3D Navier-Stokes and Euler equations. In particular, we used the method of convex integration, which has been previously applied, in particular in deterministic fluid dynamics. And we were able to obtain certain non-uniqueness results. Let me just mention briefly non-uniqueness in law, non-uniqueness of globally defined probabilistically strong solutions together with their existence, which was also open before, non-uniqueness of Markov solutions to both Navier-Stokes and Euler equations. But somehow secretly we were always thinking about invariant measures. This is maybe what is common to people in SPDEs. One would like to have invariant measures that would describe some equilibrium states. And possibly for Navier-Stokes equations in particular, one would hope to get a unique invariant measure, which would then lead to unique ergodicity. So this is what we always kept in mind. But for a long time, we didn't know how to prove that, how to get invariant measures or even stationary solutions by means of the convex integration. And then the situation changed. There was this one key idea how we can actually run a new version of convex integration, which permit us to construct stationary solutions. And then, well, as a byproduct of convex integration, one usually or always gets also a non-uniqueness result. So as a byproduct, we get non-uniqueness and also non-unique ergodic stationary solutions. Okay, but I will be more precise about everything. So let me start right away. Here I have the equations that we are interested in. So these are the Navier-Stokes equations perturbed by an additive stochastic noise. B is a trace class Brownian motion, which is defined on some probability space. Then the main unknown of the equation is the velocity u. You see that now it becomes a random variable. So it is a function of omega, r is the time, and T3 is the three-dimensional torus. So we work with periodic boundary conditions. Since we are thinking about stationary solutions, we just take time to be a real variable. So we don't consider any initial conditions or similar. Yeah, then there is a second unknown. This is the so-called pressure P. This is a scalar valued variable, and this is the Lagrange multiplier, which corresponds to the divergence-free constraint here. Then we see the viscosity constant nu. For Navier-Stokes equations, it is positive, and then if we take it equal to 0, so the Laplace term does not appear, we have Euler equations. Then you also see a nonlinear term on the left-hand side. This is a quadratic nonlinearity, and this is exactly the troublemaker for Navier-Stokes and Euler equations, but it's also the term that makes them so interesting and so puzzling. And when one thinks about turbulence theory, looking in the physical literature, it turns out that what is particularly relevant is the high Reynolds number limit, meaning that the viscosity goes to 0. So this describes the highly turbulent limit regime. In the limit, we should have the Euler equations, at least in some sense. And this should be an idealized model for turbulence. So this is what gives us motivation to study such equations. And in particular, we really want to focus on this vanishing viscosity limit, so nu going to 0. But thinking about turbulence, it turns out, and this was seen in experiments, that exact trajectories of solutions are not suitable for predictions. The reason is that everything is very sensitive to perturbations. In particular, if I change my initial value just a tiny little bit, it all gets amplified through the nonlinearity, and I get a very different result in the end. So this applies to initial conditions, boundary conditions, or even some external perturbation. Yeah, in experimental world, it's basically impossible to have exactly the same starting conditions. But it turns out that the statistical properties of solutions, so if we look at certain averages, these become well reproducible. So this is what shall be better for predictions, because we want to make predictions based on evolution of these equations. And this is precisely the reason why we want to study stationary solutions. And the stationarity that we adapt in this paper is we look at the whole trajectories. So I take u, and now I don't fix a particular time t here. You see that I still see it as a function of time. So I take the full trajectory and I shift it in time. And then this is a random variable on the space of trajectories, so functions of time and space. I look at its law, so the push forward probability measure on the space of trajectories, and I postulate that it does not depend on t. Yeah, so for all t, it's the same as if I had there 0. I get the same probability measure. So this is slightly different from, well, usual notion of invariance of stochastic processes, but one can go from one to the other. Yeah, and here we also see already what our space of trajectories is. So the solutions would be continuous in time with values in L2. And I will also be more precise about the exact regularity class that we are in. Let me just say at this moment, we will also have some time regularity and some spatial regularity. Okay, so this is for stationary solutions. And the basics of turbulence theory, of the physical turbulence theory, were laid down by Kolmogorov in 1941. This is a physical theory which takes certain hypotheses, so they postulate how things should be, and based on that they make predictions. And indeed, this was confirmed by experiments to a large extent. However, when it comes to rigorous mathematics, and that's rather surprising, that's why these equations are so interesting, really not much has been proven. And for us, the key problems of interest are the following. So on the one hand, what we are interested in is existence and uniqueness, or possibly non-uniqueness, of the so-called ergodic stationary solutions to the Navier-Stokes equations. And throughout my talk, I will denote U with the index nu to be a solution to the Navier-Stokes equations with viscosity nu. I will also tell you what ergodicity means on the next slide. Let me just say at this point, there are like better stationary solutions which satisfy certain nice property, which is again postulated by physicists. Okay, so on the one hand, this is what we would like to do. When it comes to existence, existence of stationary solutions is a classical result by Flandoli-Gontarek. When it comes to uniqueness of and the corresponding ergodicity, this was also proved in some settings. I will get to that. But we are interested in the highly turbulent limit regime, meaning we want to take the viscosity going to 0. So formally, we should converge to the Euler equations. But the question is, again, how to prove this rigorously. So we want to establish relative compactness of these stationary solutions constructed above, relative compactness when the viscosity vanishes. Yeah, and we want to prove convergence towards a stationary solution to the Euler equations. A related problem is the so-called anomalous dissipation. I will also explain to you. It's somehow an unexpected behavior along this vanishing viscosity limit. And finally, we also want to say more about the stationary solutions to the Euler equations. So again, existence and possibly non-uniqueness of these ergodic stationary solutions. So these are key problems. I mean, there are further key problems, but these are the key problems that we were able to address in a certain setting for a certain class of solutions. Up to now, what was known in this list of questions, they were only answered in some simplified settings. For instance, shell models of turbulence or passive scalar models of turbulence. But the physically relevant problem are related three-dimensional Navier-Stokes and Euler equations. And I have already mentioned a little bit ergodicity. There is the so-called ergodic hypothesis, which is really the basic assumption taken by physicists and engineers, and they basically postulate it and take it for granted. Yeah, mathematically, this is what we would like to aim for. We would like to prove that it holds, and possibly for all solutions. But let me explain. So it states that time averages along trajectories converge to ensemble averages with respect to some probability measure. What I mean is what is written here on this line. So we take some observable f on the state space. You could think of L2 norm squared, for instance. That's the kinetic energy. Yeah, so some observable that you would like to compute based on your velocity. You plug in their velocity at time t, and then you average in time. And you send capital T to infinity. Yeah, and the point is that this should converge to some ensemble average, so average of some probability measure nu. I just realized that nu is my viscosity and also the probability measure here. So sorry about that. And you integrate this observable. Okay, and now the question is, of course, does this hold true? Does this hold true for every solution starting from every initial condition? Or in which sense can we actually interpret this equality and be sure that it works? Yeah, this measure on the right-hand side then becomes invariant for the dynamics. And this leads again to stationary solutions. In a sense, if you start from this measure at some initial time and you evolve the equations, well, the law of the solution at each further time would be the same. So this is also a notion of stationarity. And then for ergodic stationary solutions, we know what should be written here on the right-hand side. Yeah, so on the right-hand side, there is expectation of the solution at time 0. And you see, I said it's a stationary solution, so actually I could take any arbitrary time here. Yeah, so in this case, this is the ergodic property for this particular solution. And ideally, we would like to say that we can put any solution here on the left-hand side, and we would have just a right-hand side given by one measure. Yeah, this would be the ideal situation, and this is indeed true in case you can prove unique ergodicity. Yeah, okay, well, true to some extent. Again, one has to be careful how one interprets the left-hand side. But yeah, anyway, this would be the ideal situation. For 3D stochastic Navier-Stokes equations, there are indeed some uniqueness results, uniqueness of invariant measure. And these were proved by the Prato de Puch in 2003. This is based on an analysis of the Kolmogorov equation, and also by Flandoli-Romito later in 2008, which is based on a Markov selection. So now you may wonder, well, this looks like a contradiction to the theorem that I want to show you. It is not a contradiction, well, for several reasons. One of them is they prove unique ergodicity for a selected Markov process. They don't exclude the existence of another Markov process with possibly another invariant measure. Yeah, and indeed, in our previous or one of the previous works with Ronchen and Shenshen, we proved non-uniqueness of Markov processes associated to the Navier-Stokes equations. But at the time, it was still not clear whether maybe they could have only one invariant measure. So now we also show there are multiple invariant measures. Yeah. And let me also mention here, and we will see on the next slides why it is so, that even existence of stationary solution, so let alone ergodicity and all further results, only existence of stationary solutions to stochastic Euler equations was unknown up to now. Okay, and so I want to explain to you or give a hint how usually stationary solutions are constructed, and also time-evolving solutions. So I take here Navier-Stokes equations without any noise, just for simplicity. Okay, I put here time from 0 to infinity, but it's not very important. Actually, we won't see it here. The question of a priori estimates. Typically, how one would like to construct solutions is to build some approximation, maybe a Galerkin approximation, derive some uniform estimates, pass to the limit. Yeah, for this, one would like to apply a chain rule. Yeah, so in deterministic setting, this translates to testing the equation by the solution itself. For this, to do it rigorously, I need to assume that my solution is smooth. And that's why I put it here in red, because this is really what we need to keep in mind here. I assume that there is a smooth solution, and then I test the equation by U. So I just multiply, there is an inner product in L2, and let us take a look what we obtain here. On the right-hand side, we have the Laplace term. We integrate by parts, and we obtain the red term here. So the L2 norm of the gradient square. From the pressure, we can use the divergence-free constraint, and the term vanishes after integration by parts. The same happens here for the convective term. Again, we integrate by parts, and we use the structure of the nonlinearity, and the term drops out. And from the first term, we get 1/2 of the time derivative of L2 norm squared. So you see, if the solution was smooth, then I get the so-called energy balance, energy equality. And I could think of doing exactly the same computation for Euler equations, meaning nu is equal to 0, and I get the so-called energy conservation for Euler equations. So you see, this means that the energy at time t is the same as the energy at time 0. And this is really an idealized situation because of this assumption. Yeah, and if we compare now these two energy equalities, if we also assume that we were able to perform the vanishing viscosity limit, so send viscosity to 0 and really pass to the limit also in these energy equalities, that would imply that the limit of the red term is 0. So this is what we would expect in case we have nice and smooth solutions. Yeah, so what this means, viscosity goes to 0, so the gradient can blow up, but not too much. It must be killed by the viscosity so that the limit of the product is 0. In other words, the limiting solution cannot become too irregular, because the gradients don't blow up too much. Yeah. Okay. So this is an idealized situation. This would be like a formal limit from Navier-Stokes to Euler, but it turns out that such good solutions do not exist globally in time for general initial conditions. On the other hand, there is a theory of weak existence theory, which applies globally in time. The notion is the so-called Leray solutions. So they exist globally in time, and they satisfy the energy inequality. So what was an equality on the previous slide, I make it into an inequality. And the reason for this is the smoothness assumption. So I cannot perform this testing by the solution on the final level. I need to work with some Galerkin approximation, which is smooth, which is finite dimensional. So it is smooth, there I can do the testing. And then the problem is I don't have enough uniform regularity to pass to the limit really in this gradient term. So I can only use lower semi-continuity, and that's why I end up with an inequality. Yeah, but still these solutions are somehow nice. They exist globally in time. And this is also the strategy. So these a priori estimates are also classically used for the construction of stationary solutions in the stochastic setting. So this is what Flandoli-Gontarek did. Yeah. And now you already see that with this inequality, there is some space for strange things happening. And the one kind of unexpected thing is the anomalous dissipation, which is predicted by Kolmogorov. And it states that the limit of this gradient square, which it's the limit that on the previous slide was 0, actually here it should be positive. So there is a dissipation rate, epsilon, which is strictly positive. And okay, I also included here some expectation, because in Kolmogorov theory, we should somehow think in terms of averages, basically to think about the stationary solutions. Yeah, so this is the anomalous dissipation, which we also address in this paper, well, in some sense. Okay, and I want to mention here one more point. So this energy inequality, this is for Navier-Stokes. And if viscosity is positive, you get really this bound for the gradient. For Euler, you lose it. Meaning, if you wanted to construct weak solutions to Euler by proceeding via Galerkin approximation, it doesn't work. Because you lose this gradient estimate, you wouldn't get strong convergence in L2, and therefore you wouldn't be able to pass to the limit in the nonlinearity. And this is also the reason why existence of stationary solutions to the stochastic Euler equations was unknown so far. Yeah, because for Navier-Stokes, we use also this estimate, and now for Euler, it doesn't work. So what we do in our paper is we work with a different class of solutions. This is not a necessarily larger class, and I will tell you why. So when it comes to spatial regularity, we are in H theta, and theta is small but positive, meaning we don't reach this gradient L2 by far. So this is where our class is kind of bigger. On the other hand, we have here continuous function in H theta. But moreover, we have Helder continuous functions with values in L2. And this is better than what Larrey solutions usually have, because they're not even continuous in L2. Yeah, so in that sense, when it comes to this time regularity, we are better. But anyway, this key property, which somehow suggests that these are physical solutions, meaning this energy inequality, we cannot have it because we don't have gradient in L2. And a very important point, which is the key why we are able also to treat Euler equations, is that this regularity and also global in time bounds in these spaces are uniform in the viscosity. So the viscosity can be positive, can be 0, and the bounds do not depend on the viscosity. And as I have already mentioned before, we use a new stochastic convex integration, which compared to our previous works is now somehow more honest stochastic. Previously, it was maybe more semi-stochastic, and now it is more stochastic, and it helps us to prove also results about stationary solutions. So let me tell you more. The convex integration is an iterative procedure. It is an explicit construction of solutions scale by scale. The method that we use was developed by Buckmaster, we call. And they used it to prove a non-uniqueness of weak solutions for deterministic Navier-Stokes equations. In the stochastic setting, we do several modifications. And I mean, on this slide, you wouldn't really see the reason why I say it's an honest stochastic. This will be seen on the next slide. What we do in the first step, we want to somehow separate the difficulties. This is step which is used in many SPDE results in all areas. So we split the solution into the stochastic part and the nonlinear part. The stochastic part Z solves a linear Stokes or heat equation. Yeah, so I put the noise here, keep the Laplacian, and for reasons of stationarity and global in time estimates, we also add this damping here, which gives us a stabilization as t goes to infinity. Okay, and then the rest goes to V. V doesn't have any noise because that's all in Z already. So V satisfies a deterministic PDE, or I should say random PDE, but there is no stochastic noise. However, there is a nonlinearity. So the full nonlinearity from the Navier-Stokes equations is now written here. And now we want to apply an iteration on the level of V. So we come up with an iterative procedure, and on the level Q, Q is the parameter that indexes the iteration, so it is a natural number. We take basically the same equation. For Z, we replace by ZQ, which is like a Littlewood Paley projector to some frequencies depending on Q. So in a sense, I want to approximate the Z here by putting there something smoother and also frequency localized. Yeah, but with that, I cannot still solve the real Navier-Stokes equations. I need to add an error. So it's like on the level Q, I solve the equations up to some error. This is called the Reynolds stress. And the point is that in the limit, I want to construct this sequence of VQs so that they converge, so that there is a limit, so that I can pass to the limit also in the nonlinearity, and so that the RQs, the stresses, they converge to zero. Because you see, if the stress was not there, then I add this to the equation of Z, and I have solved my Navier-Stokes system. So this is like the overall strategy, but of course the key point is, how do I do this? So given V0, R0, and you can also take them zero maybe. You can take VQ0. Then how do I find VQ plus 1? And I want to find it in such a way that these RQs become smaller. Okay, so this is now the key question, and I want to give you a hint how this goes. Roughly speaking, we look for a small perturbation, WQ plus 1, so that the new iteration is given as a sum of the previous one and this perturbation. And you see, this perturbation needs to be small in some sense because I want the sequence VQ to converge. Okay, and the perturbation must be so good that the new stress, RQ plus 1, is much smaller than the old stress. Okay, so this is still nicely to say, but how do we really do it? So we look at the difference of the two equations. The equation on the level Q plus 1 minus the equation on the level Q. And this way we get a formula for the new stress. And the formula has many terms. It is a long formula, but I have picked up here only the main term, namely the one that contains the old stress, RQ. And I put there also these perturbations, how they appear through the nonlinearity. And the point is, we want to find these perturbations in such a way that the sum RQ plus WQ plus 1 all times WQ plus 1, this is much smaller than the RQ alone. Because this would give me one contribution to the new stress. But let me say there are going to be further contributions, which we also need to take care of. But this is like the key point. Yeah, and this is done in Buckmaster-Vicol by using suitable building blocks. It's done like this in any convex integration results, but the building blocks differ. So in Buckmaster-Vicol, in the Navier-Stokes paper, they introduce intermittent jets. And so these are really explicit functions, highly oscillatory, based on different parameters, they oscillate. And you should choose the parameters. And then there is a geometric lemma which permits to take a matrix like RQ, and decompose it into a tensor product of two vectors. Yeah, this is really a very simplified picture. And through this geometric lemma, we are able to construct amplitude functions A, so like coefficients that depend on RQ. We multiply these intermittent jets by them. And this is what in the end, it's really constructed in such a way that the sum here, the tensor product kind of minimizes or makes the stress smaller, like cancels the worst part, I would say. Yeah, so this is really a very simplified picture. The amplitude functions oscillate slowly, and then there are large oscillations by the intermittent jets. Yeah, and these oscillations propagate through the nonlinearity here to cancel part of the old stress. So that really what we get in the end is RQ plus the tensor product is much smaller than RQ in some norm. So here I don't want to be very precise. I mean, I don't want to tell you about the norm. I will do that in a second. Yeah, so this is, I mean, here there is again nothing stochastic. This is really the deterministic method. The stochastic contribution is somehow how to choose these norms, how to do everything basically in the stochastic setting. Yeah, and this is really a very simplified picture. So it wouldn't work like that for the Navier-Stokes equations. There is the additional modification step. There is the additional compressibility corrector, time corrector. So this W has actually more components, and I spoke here only about the principal part, and there are two other parts. And all this then leads to a much bigger formula for the new stress. Yeah, but let me leave these other points out, and let me rather tell you how it is in the stochastic setting. So we work with the following norms. Here you recognize the space. I mean, I have the spaces here. So these are the function spaces that I mentioned before. Continuous with values in H theta, and Helder continuous with values in L2. And we put like local supremum here inside the expectation. So we choose here interval t to t plus 1, but you can as well do any other bounded set. Here we have the H theta norm, and we need to include moments. Yeah, so for me, R will be bigger than 1. I put some general moment here. And then I want to think about stationary solutions, about the long time behavior. So I also include supremum over T here in front of the expectation. And I do exactly the same with this Helder space. So it's Helder locally, then expectation, the moment, and then supremum over T. So the local Helder norm does not depend on the position on the real line where you are. Yes, we can also say the solutions will have uniform moment estimates locally in these spaces. In our previous papers on stochastic convex integration, we worked with stopping times, meaning we introduced stopping times that would control the noise uniformly in omega, and we used these estimates in the convex integration. So we didn't use any expectations. And actually, we thought for a long time it's not possible to use expectations. And the reason being is that there is the quadratic nonlinearity. And so if you try to estimate the new stress, the estimates become superlinear. So you cannot, it's not enough to control just one moment, one R. It turns out that what you can do is to fix one moment R. So we fix R bigger than 1, which we want to control, really make vanish. But we need to keep track of the bounds of all the other moments as well. The reason is that they appear in the estimates. Yeah, and so here I want to show you a sample of these iterative estimates, namely those on the stress. There are further iterative estimates on the velocity and on the difference of the old velocity and the new velocity, etc. So we work here for the stresses with similar norms. We put local supremum inside the expectation, then we have the moment. Important here is that we work in L1, and we have the supremum over T outside. Yeah, and this should be bounded by some number. Well, the point that you need to know here is only that delta Q goes to 0. So this is really what gives me vanishing of the stresses as Q goes to infinity. But as I mentioned, we have to keep track also of the bounds of other moments. So we put here a general M, and then we have such a bound. So I don't want to scare you. I just wanted to show you that one needs to be fairly precise about these bounds. Yeah, because they really appear in the estimates, but of course also in the estimate of the rth moment. There would be M moment appearing for some M large. So like I would have this large constant there. But the point is that there is always something that makes it small. Yeah, that this bound would then be multiplied by something, and this could be so that this large constant can be absorbed. Yeah, maybe you're wondering what is this L? So L is related to bounds of the stochastic process Z. Yeah. Okay, so these are somehow the main idea, and it's very subtle, it's technical, and one has to be careful about all these constants and about all these moments, so that really all the terms where you need to use higher moments get multiplied by something which is small, which can absorb this blow up. So this is the main idea. Yeah, and here's the result. So let R bigger than 1 be given. So this is the moment that I want to control, really have the stress vanishing in this moment. And I am given a smooth energy. So this is a function of time, and it has a compact range in 0 infinity, meaning it is bounded above and below by positive constant. Then there exists theta, so regularity exponent, so that for every viscosity, strictly positive or 0, there is an adapted process, U nu, which belongs to this regularity class, and it solves the stochastic Navier-Stokes or Euler equations. Moreover, these norms that I have introduced on the previous slide, so norms in these spaces, they're bounded uniformly in the viscosity. And finally, we could prescribe the kinetic energy. So the function E was given, and our solutions have this function as a kinetic energy. So this is existence of such a solutions, but you immediately see this also gives a non-uniqueness, basically by choosing different energies. Here. And these estimates, also I should say, there is this word adapted. So the solutions are really probabilistically strong. We don't change the probability space. We construct the solutions explicitly on the probability space where the Brownian motion is given. And they're analytically weak because, well, we don't have enough regularity to say the equations are satisfied in a classical sense. So still, as I mentioned before, the regularity theta is positive, but is small. It's not 1 in particular. And the bounds were chosen in such a way so that we can use these solutions now for Krylov-Bogolyubov and for the construction of stationary solutions. Exactly. That's why we have, that's why we have chosen R bigger than 1, so that we get enough integrability in omega, and we have this global estimate by having the supremum over T. So by Krylov-Bogolyubov, and I will explain to you again more in a second, we get existence of stationary solutions. Then actually, the bounds are so good that we can even apply Krein-Milman theorem to get existence of ergodic stationary solutions. And we get non-uniqueness of the above by choosing different energies. So I can, for stationary solutions, I need to choose the energy constant, so independent of time. Because if I aim for a stationary solution, then the left-hand side here does not depend on T. But choosing different energies, so different constants, positive constants K, I get different ergodic solutions and I get different stationary solutions as well. So this is how we then conclude the uniqueness, the non-uniqueness, how we actually get it as a byproduct. And there is still one subtlety which you may be wondering about, namely how to apply the Krylov-Bogoliubov. Because the way this is usually applied is you have an SPDE, and it is a fairly nice SPDE. So you have existence, you have uniqueness, you have continuous dependence on the initial condition, meaning you have the Feller property. And then you can apply Krylov-Bogoliubov. So you see, we don't have uniqueness. So first of all, the usual Markov semigroup is not defined. I mean, we could construct some Markov processes, but this is not what we want to use here. We rather work with shifts on trajectories. So we replace the Markov semigroup by the following semigroup, which takes a trajectory. So in terms of velocity, it is continuous function in L2, as we have seen before, and it shifts it in time. And for the Brownian motion, I have to do such a shift so that it remains a Brownian motion. So we replace Markov semigroups by this. Now, the huge advantage of these shifts, shift semigroup, is that we get continuity for free. And this is really to be compared to the Feller property, which is very difficult to obtain. And I mean, in the for the Navier-Stokes, well, at least in this setting, we don't have continuous dependence on initial condition. So we cannot prove Feller property. But we can somehow overcome this by working with these shifts, and they are continuous. So in this setting, we are able to apply Krylov-Bogoliubov. So we apply it to the ergodic averages, where here I have the law of these shifts. Yeah, and I use my global in time estimates to get compactness of this. They're also sufficiently good so that I can pass to the limit in the equations. So I get an existence of a limit for a subsequence at least, and the limit is shift invariant. So it's again invariant with respect to these shifts. And it is a law of stationary solution to the Navier-Stokes, or if we work on the level of Euler or to the Euler equations. The ergodicity is then understood as ergodicity of the dynamical system T with these shifts and this invariant measure. And I want to point out once again that these bounds are really also uniform in the viscosity. So in particular, these results apply to the stochastic Euler equations, but also to the vanishing viscosity limit in the setting of stationary solution. So for the first time, we could also say something about this limit rigorously. When it comes to the anomalous dissipation, we do not obtain directly anomalous dissipation for the vanishing viscosity limit in the Navier-Stokes system, but rather we use convex integration, and that's why we need to include these Reynolds stresses. And so we have an anomalous dissipation result for vanishing viscosity limit in Navier-Stokes Reynolds system, where the Reynolds stresses vanish in the limit. But I would like to stop here, and I thank you for your attention.
Thank you very much, Martina, for a very interesting talk. Are there any questions? Yes, please, Emanuela.
Thank you. Hi, Martina. Thank you for the nice talk. I have a question on the noise. If you put the transport noise, do the structure break?
Yeah, we don't know yet. Okay. So at the moment, it seems that we can apply convex integration to Euler equations with transport noise. The result is not, the paper is not yet finished. But for transport noise, one really needs to think how the blocks, how the building blocks here would look like. And for Euler equations, we were able to somehow modify them so that we can accommodate transport noise. For Navier-Stokes, I don't know yet. So the question would be really how to get this step working, how to design the blocks so that also transport noise can be handled.
Thank you very much.
Any other questions? I wanted to ask about the stationary measure. Measures. Yes, there are many of them. Yes. So, but you don't. Can you say anything? Can you say that there exists at least one such measure that is non-degenerate?
So what do you mean non-degenerate? I mean, the measure, I have a prescribed L2 norm squared. So the measure is somehow, I mean, if it is Dirac or not. No, I don't know what you mean. So for instance, for deterministic Euler equations, we also prove that these stationary solutions are genuinely random. So they're not just Dirac sitting on some time-independent deterministic solutions. Yeah, so the solutions to deterministic Euler equations, which we can also construct via this method, they can be done really randomly. So there are honest random solutions.
But you can't say much about the support of this measure. Yes, it's not one point. Yes, that you know.
No, the only information that we have comes from this regularity class that we are in. Yeah, so that's an interesting question, but so far we don't know. That's really all we have at the moment.
Okay, there is also, there is one more question, Christina.
Sorry, thanks for the good talk. I wanted to ask, under the constraint of the energy, is the solution unique? For a given energy, for a given K, do you have only one solution?
Yeah, we don't know yet. So this is one good point that I forgot to mention. In these results on unique ergodicity, they work in the class of Larey solutions. So they always have the energy inequality. So in that case, they have really, for each Markov selection, they have unique invariant measure in the class of Larey solutions. And so they have a different class of solutions.
Okay,
but for
thanks.
like say deterministic Navier-Stokes with a force, so particular force, there is a result also on non-uniqueness of Larey solutions, but with a force.
Thank you.
Are there other questions? I think David has a question. But he did not raise his hand. He sent question in the chat. David, would you like to ask the question?
David has maybe no microphone, so he was writing his question in the chat, so maybe I read it. Can you expand further on the decomposition trick? It seems analogous to the D'Aprato-Debusque trick, it seems.
Yeah, exactly. This is basically, this is related to D'Aprato-Debusque trick. Yeah, how it is used. That's why I said it's used in many areas of SPDEs and frequently used, because it has the benefits that you split the difficulties. So on the one hand, you have Z, which has all the noise, but it's a linear equation, so you have a lot of information about it. And then on the other hand, you have the nonlinear equation, where, okay, there is this additional Z term. But yeah, this is really also the reason why it is used in singular SPDEs. We also used it at some point for regularity theory, even for quasi-linear SPDEs. So it has really many benefits, which was seen in the literature very often. Here, so in our previous works, we don't put this damping term there. This is there for the global in-time solutions. Yeah.
This is something that has been done earlier by Flandoli, I think, with arbitrary alpha instead of 1, and then it improves the speed of convergence to the limit.
Yeah, exactly. I think it was the paper on the random attractors where they also did. Yeah, because then if you think of the energy estimate, so testing this equation by the solution itself, there is one minus here and there's another minus, so you get a plus. So you get an additional term in the energy inequality, which gives you the global in-time estimates. Yeah, and so another reason why this the Pareto-Debye trick is used often is that here I have a stochastic noise. So I need to use stochastic methods how to estimate the solution. On the other hand, for the second equation, there is no stochastic noise. I can really work pathwise. So for V, I can fix omega and then get some estimates, possibly. However, here we have seen that to be able to construct convex integration solutions that are good enough for stationarity, we need to work with expectations anyway. So we cannot just work pathwise as we did in our previous works.
Mm-hmm. Are there any other questions?
Then I have a question.
Yeah.
Martina, thanks for the nice talk. So you say there is one theta larger than 0. So the theta is smaller, strictly smaller than 1, is it right?
Yes, that's correct. It's possibly very small.
So, but can you say something more about the theta? Can you make more conditions that thetas can become 1? Or it has to be strictly smaller than that it works?
Yeah, it's really small. So we get it somehow during the convex integration. Yeah, like in these estimates. So we need to prove the iterative estimates for the new stress. And you get many terms that are parts of the new stress. And at many places, you need to choose certain parameters. And it's like, so there is a number of places where you say, okay, and we choose beta smaller, B bigger, A bigger. And the final limit that we get then depends on this, on these parameters. So we get it then by interpolation. Yeah, so one could possibly say something more explicit, but I mean, in the end, it would be small, like small.
I see.
Yeah.
So,
and like getting, sorry, one more point, applying convex integration to get these Larey solutions to really have gradient in L2, this is like a big open problem. And also in the deterministic setting, this is not done. I mean, yeah, people also say that it's not possible to reach this level by convex integration.
I see. Okay.
So these solutions cannot be that good to have gradient in L2.
Can you say something about the dimensionality of the stationary solutions? So you mentioned in your last result, okay, for any energy level, you choose a parameter key. So you have here one dimensionality here, at least in this result. So if you choose ET equals K and you vary K, so for every real number. But are there other parameters which impact basically the dimensions of all stationary solutions?
Yeah, there is another point which I can prescribe. This is what we did in the deterministic setting, because for deterministic Euler and Navier-Stokes, we wanted to prove that these solutions are also genuinely random and time dependent. Because, for instance, for deterministic Euler, there is a large number of explicit steady state solutions, and they could, of course, also be somehow put together to be random. But we could construct stationary solutions based on this method that are also time dependent. And basically, there is even more. We prescribe a stochastic process, which is stationary, smooth trajectories, and we construct the convex integration stationary solutions somehow near to this process, so that the distance to the process in a suitable norm is smaller than a given epsilon. So it's not like we prescribe exactly the value, but it's like, in a sense, I can prescribe some almost statistics, like I give myself a stochastic process and my solutions would have similar statistics or somehow almost similar statistics. And in particular, I can construct the solutions to be close to a Gaussian process or to non-Gaussian or to pretty much anything I want. But it's closed in a suitable norm, but as close as I wish. Yeah, so maybe answers partly your question, that somehow there is like a lot of freedom, I would say.
Yeah, no, this answers my question. Yeah. Thank you so much.
You're welcome.
Martina, can you show again the slide where you have moment estimates?
For the R?
For M, you have M. Yes, that's here, yes. So in the second estimate is for what? For any M greater than R?
Yes.
Yes, you say for any M, this is written. So this is quite nice, yes, because you have nonlinear term and you have estimate expected values, and you can do this for any moment you like. Can you comment about how you can obtain this?
Yeah, like you see, the problem is that here we are on the approximate level in the iteration on the level Q, and this all blows up as Q goes to infinity. So in the limit, I cannot control the moment. This goes to infinity.
Okay.
Yeah. But I mean, as I can choose R as large as I wish. So I can control finite moments. I mean, in the sense that not only control, but the constant goes to 0. Yeah, so for the limiting solution, I would then control this rth moment, and R is chosen, but it must be finite. It's not that I can control all the moments.
But it can be as high as you want, yes? So this is still a nice...
Yes, exactly.
Okay, thank you. Are there any other questions? So if not, then let us thank Martina again for a very interesting talk, and everyone is invited to coffee break. You should have received the link to the coffee break, and we can meet there again in a few minutes.
Yeah, perfect. Thank you.
Thank you. Bye.
Thank you. And I close the session. Thank you, everybody.
Yeah. Bye.
Bye.
Thank you.